Hello everyone, this is Manoj Yadav. Today we are going to discuss the torsion of shafts. See what is torsion? When a structural member is subjected to some movement about its longitudinal axis, the member tries to twist. It tries to twist just like the claws, wet claws are twisted by us uh, for being drying. In a similar way, it tries to twist the shaft or structural member. Thus, shear stresses are induced in each and every section of the member. Such a mode of loading is called torsion, and the twisting movement is called torque. A shaft gets distorted when its one end is made fixed and another is subjected to some force. As shown in figure, one end of the shaft is fixed and at the other end force is being applied in form of torque. So T equal to F into L. Now we will discuss the pure torsion. See, whenever a shaft is loaded, it is subjected to two types of stresses. First one is torsional shear stresses due to the transmission of torque, and another one is a bending stresses due to the weight of pulleys, gears, etc. Now, the condition of shaft in which the stresses are only shear stresses, that is no bending stresses are there, that condition of the shaft is said to be pure torsion. Now before going to the derivation of bending formula, we have to assume some facts. These are known as assumptions. So assumptions of torsion are: first one is material of shaft is homogeneous and isotropic, that is material must show same properties in all the directions. Second one is pure twisting movement is applied at the shaft, that is at the when the shaft is loaded, there must be no bending stresses, only pure torque must be there. Third one is a shaft circular in section remains circular after section. Now twist is uniform along entire length of the shaft. There is no change in the length of shaft. All radii which were straight before torsion remains straight after torsion, and the cross sections of shaft which were plane before torsion remains plane after torsion. These are some of the assumptions of torsion. Now we will derive the torsion formula. As all of you know, the torsion formula is given by T by J equal to tau by R equal to G theta by L. So we have assumed a shaft of length small l. One end of the shaft is fixed and at the other end of the shaft torque is being applied. Now due to the application of this torque, the shear strain is developed in all the sections of the shaft. Another view of the shaft is shown in figure, where the angle of twist is represented as theta and the radius of shaft is capital R. Now shear strain is given by phi equal to AB upon L, as shear strain equal to transfer displacement upon height, and transfer displacement in this case is AB. So we can write phi equal to AB upon L. Now another view of the same shaft shows the arc AB is equal to radius multiplied by theta, R theta. So we can write shear strain phi equal to R theta by L. Now according to the Hooke's law, shear strain tau is directly proportional to shear strain phi. So tau is directly proportional to phi, or we can say tau equal to G phi. Hence phi can be written as tau by G. So putting this value in this equation, tau by G equal to R theta by L. Now rearranging this equation, we get tau by R equal to G theta by L, which is the first part of the derivation. Now this equation shows that shear stress at center, when R equal to 0, the shear stress will be 0, and when R equal to maximum, the shear stress will be maximum. So it shows that at the center of the shaft shear stress will be 0, and at the periphery of the shaft shear stress will be maximum. This is another same shaft. Here at radius r, shear stress is tau, and we have assumed a small strip at a small r distance. The thickness of strip is dr, and at this thickness, let us assume the shear stress is tau r. So we can say tau r uh, divided by small r is equal to tau by r, since the ratio of the shear stress and radius is constant at all the sections of the shaft. So we can say tau r equal to tau into small r upon capital R. Now, due to this shear stress at the strip, a shear force will be there, which will be dF equal to shear stress tau r multiplied by dA. This dA can be written as 2 pi r dr. So we get dF equal to tau r into 2 pi r dr. Now this shear force will create a turning moment at the center. The turning moment dt equal to dF multiplied by r, that is tau r multiplied by 2 pi r square dr. Hence the total torque T equal to integration of tau r into 2 pi r square dr. Now putting the value of this tau r as tau into small r upon capital R, we get T equal to integration of tau by r into 2 pi r cube dr, or tau by r 2 pi r to the power 4 by 4. This term pi r to the power 4 by 2 is called polar modulus, or it is represented by j. So we can say T equal to tau by r into j. Now rearranging this equation, T by j equal to tau by r, but from our first part tau by r was equal to g theta by l. Hence we get the total equation or total torsion formula as T by j equal to tau by r equal to g theta by l, where T is the torque, j is the polar modulus, tau is the shear stress, r is the radius of shaft, g is modulus of rigidity, theta is angle of twist, which is always taken in radian in this equation, and L is the length of the shaft. For a solid shaft, by equation T by j equal to tau by r, we can get torque for solid shaft T equal to pi by 16 tau d cube. Similarly, for a hollow shaft, torque is given by T equal to pi by 16 tau d naught to the power 4 minus di to the power 4 upon d naught. Now, whenever you replace a solid shaft by a hollow shaft, the necessary condition for the replacement is torque transmitted by solid shaft must be equal to torque transmitted by the hollow shaft, that is Ts must be equal to Th. Now, whenever you replace the solid shaft by hollow shaft, some percentage saving must be there in the material. This percentage saving in Ws minus Wh upon Ws into 100, where Ws is the weight of solid shaft, Wh is the weight of hollow shaft. Now the polar moment of inertia J is given by J equal to pi by 32 d to the power 4 for solid shaft, and J equal to pi by 32 d naught to the power 4 minus di to the power 4 for hollow shaft. Another formula which we will use for determining the value of T will be P equal to 2 pi Nt by 60, where P is power in watt and T will be torque in Newton meter. Now here are some small definitions related to the torsion. First one is torsional stiffness. It is defined as the torque required to produce unit twist. See, we know the formula T by j equal to g theta by L. We can write it as T by theta equal to gj by L. This term T by theta, it is known as torsional stiffness, or we can say the torque required to produce 1 degree of twist, that is known as torsional stiffness. Another one is torsional rigidity. It is defined as the torque required to produce unit twist in unit length. Now we know T by j equal to g theta by L. By rearranging it like in the way T divided by theta by L equal to g into j. This term g into j is known as torsional rigidity.